Thank you so much for this absolutely wonderful introduction. Wow, I don't even know what. There's a lot of expectations right now. So what I'm going to do is going to tell you about what we're doing about creating practical, real-world quantum computers. And that's really hard. And you can't, not one person can do that, not one company can do that, not one university can do that. And so I'm also going to tell you about our efforts to actually really capitalize on what the region has to offer, the vacuum companies, the electronics companies, all the amazing software activity in Brighton. What we're doing is trying to create a whole quantum Silicon Valley, and apologies for the use of Silicon Valley, but people understand what that means. And our efforts to trying to put that together and really bring people from all around the world helping us to create these truly amazing machines. So, but let me start first. What actually is quantum? And quantum, you could think of as strange, very counterintuitive. Einstein called it spooky. And why? Because you could be sitting here and you could be sitting over there simultaneously. So an object can be at two different places at the same time. Now, most of us will think that is science fiction, maybe some kind of beam me up, Scotty, Star Trek kind of thing. But in our lab, we can actually make this happen on a daily basis. And my PhD students, they actually literally do this every day. And I've been doing this for 25 years now, and it still blows my mind. So there's superposition, an object being at two places at the same time, and there's entanglement, which is even stranger. It's a very strange correlation where something that you do here affects instantaneously an object on the other end of the universe or in the United States or anywhere else without these objects actually communicating. Now, quantum physics has mystified scientists for many years, and they explored, carried out experiments. But maybe around 10, 15 years ago, they thought about, can we tame these very strange phenomena to build machines that have a capability that a classical machine could never have. And what are these machines? They are machines that can compute things that would take even the fastest supercomputer in the world millions or billions of years to solve. They are quantum technologies, also imaging technologies, where you can see things that you cannot see with any other technology, which are, these sensors are so sensitive they can detect things, maybe even signals of the brain, which you couldn't detect in any other way. And timing systems, there's actually a whole raft of applications in quantum technologies, and this is a extract from the UK's National Quantum Technology Programme, Strategic Intent. And you can see that goes all the way from creating new pharmaceuticals to thinking about how we solve challenges like dementia, over navigation, helping us to overcome challenges when a GPS just doesn't work anymore, all the way to finance, or to help us understand how we can use less energy. For example, 2% of the world's energy is being used to make fertilizer. Is it possible to reduce that energy? Now, but I don't want to just give you the science. I should also tell you how impactful that field is in terms of economic prosperity. Now, Oxford Economics predict that there are going to be 148,000 jobs in quantum computing in 2055. Indeed, they predict that 212 billion pounds will be added to the gross value product. And that's not because of just the quantum industry, but that's because of the enhancement of productivity across nearly any industry sector. That ranges from pharmaceutical industry to the chemical industry, to transport, to defense, to everything you can possibly imagine, even financial services, portfolio optimization, things like that. All of these things are actually really impacted by the emergence of quantum computers and other quantum technologies. So here in the UK, we're actually in a hotbed of the development of these quantum technologies, and usually you'd think it's probably going to be the Silicon Valley, United States, but it's actually the UK which has been really pioneering. And this is also reflected in the investment, in the private sector investment into quantum technologies. You can see there's a really exponential curve of investment into the development of quantum technologies. So how does that all relate to Greater Brighton? Here in Greater Brighton, we have the Sussex Centre for Quantum Technologies, and in this research centre, we develop quantum clocks, quantum networks, quantum computing, quantum sensing, quantum simulation, and quantum imaging. And this is one of the biggest centres in the UK to develop this technology. And just to give you a bit of a feeling what kind of things have come out of Sussex. Sussex is the largest centre in the UK and one of the largest centres in the world for a particular technology called ion trapping, where you hold individual atoms on a microchip and use these atoms to store quantum information. We were first to strongly couple an ion with a photon, which gives rise to the quantum internet. So that's something where you can really repeat what we've done with the internet, but do this in quantum physics, for example, create very secure communication. Many years ago, we've led a consortium from Google, Riken, and other universities, and we published the first industrial blueprint of how you go about building a million or billion qubit quantum computer. Now, you may have heard of Google, IBM, all these companies around the world working to build quantum computers, but the number of qubits these machines contain are nowhere sufficient to realize any of the interesting applications. So what we've invented here is a technique to scale this technology up to useful number of qubits, to millions of qubits. And there's many other things you may have heard on the news a couple of weeks ago. We just had a breakthrough and we achieved here the world record in sensing tiny electric fields. And what that means is, using this technology, you could imagine sensing electrical signals, pulses in the brain, and therefore then correlate that to things like sensations, or even think about the origin of mental illness or consciousness itself. So these technologies are really far and wide. One of my colleagues, in fact, has come up with an experiment that is now run on the space station. So this is really a tremendous hotbed at Sussex for quantum technologies, but not just for the research, also in training. Here at Sussex, we, as a world first, or certainly as a UK first, we created a degree where undergrads from day one don't just do the training and the modules and the coursework, but can also participate in one of our research groups. So learning on the job, learning as an apprenticeship on making quantum technologies a reality. We also pioneered in the first online distance learning degree where you don't need to be in Brighton, but you can be anywhere and learn about quantum technologies from the comfort of your home. And last year we awarded a 24 million doctoral training centre where we, together with the University of Bristol, where we really work to train a workforce for this new quantum technology sector. So this is really exciting to have these connections and to really bring about people into this sector, because it's an extremely fast-growing sector. But it also means we need to work with our community. And I'll give you some examples. This morning, I was opening the Mid-Sussex STEM Challenge, and quantum is actually a fantastic way to motivate students to bring about, to enter STEM, to learn about STEM, and to motivate that science is just right now at the beginning and doing these degrees. We've curated an exhibition at London Science Museum, and we also actually did something really bold. We placed a walk-in quantum computer right in the middle of London's financial district. So, I don't know, we don't have sound. Do we have sound? So what you see here is... you can possibly imagine. Building a quantum computer is really the holy grail of science. And what we've done today here is exhibiting what we're going to do for the next 2 years. This blueprint, how to construct a large. We showed people how the prototype looks like, and we've shown people how it works. And so yeah, I'm very excited to be part of a fantastic team. My team at the University of Sussex, we're gonna build a quantum computer. So there's a lot of research at the University of Sussex, but I want to now tell you a little bit about one particular area that we develop at Sussex, and that is quantum computing. And so at Sussex, as I mentioned, we really take active steps to develop and invent a technology that will enable quantum computers, not just with hundreds of thousands of qubits. This is where the state of the art right now around the world, but where we really work with millions of qubits. And I can't do that myself. I actually got a really, truly amazing team who is really helping us to make some of these unbelievably difficult challenges, overcome these challenges and make this technology a reality. So, but let me talk, what is a quantum computer? It changes the scaling, how long it takes to solve a certain problem. And what that means is that you don't just have a faster computer, but you have a computer that can fundamentally solve things that a classical computer could just never do, where you just say, okay, would be 1,000,000 years, but that's obviously not something you're going to run on a computer. So what are these problems that a quantum computer may be able to solve? Nitrogen fixation, as I mentioned, to make new fertilizer consumes 2% of the world energy. Imagine you could reduce that. What would that actually mean for energy consumption? We work with Rolls-Royce to help them develop more fuel-efficient aircraft engines. You could think about portfolio optimization finance. Something that really sits very close to my heart is the idea and the possibility that you can rapidly speed up the development of pharmaceuticals. Because here, it takes you typically 10 years and over £1 billion, and most of these things don't work at the end. Now imagine you can have a machine that could accelerate this process. Instead of 10 years, maybe 3 or 4 years, instead of 1 billion, a fraction of that cost. Now, that sounds like a big promise and is actually unbelievably difficult to make such machines. And I'm going to show you how are we going about making these machines. So each bright dot that you see here on the screen is actually a single atom, one charged atom. When you come into my lab, you can actually move these atoms with your own hand by changing the voltages. And then you can see one atom at a time moving across. And it's actually a little bit like a game of Pac-Man. Who played Pac-Man before? Perfect. So you've already worked in quantum computing. So the way how this looks like, this is a silicon microchip, and the ion levitates above the surface of the chip. And by adjusting these voltages, you can now move these ions around, as I said, just like a game of Pac-Man, and now execute computations by moving the ions on this chip and then carrying out entanglement operations on the chip in order to give rise to a computation that he couldn't solve any other way. So at Sussex, one of the things we've invented, a way to do these type of computations using microwave technology. What that enables us is to actually calculate things by just applying voltages to a microchip. And it might not be very meaningful to you. In fact, you're going to say, hey, classical computers also work by applying voltages to a microchip. But the point is that previously this technology needed pairs of laser beams for every single qubit. So you would need, for a 1,000,000 qubit quantum computer, millions of pairs of laser beams. And that would probably take the size of a city or multiple cities to build a machine like that. So you can imagine why people thought you probably can't build a quantum computer. Using this invention, using microwave technology, we made it possible to build machines much smaller and allow us to really scale this technology. The second thing we proposed together with Google and others in 2017 was, how can we make these machines modular? Because you need to make them modular in order to host sufficiently many qubits. Now, we came up with a very crazy idea, and that is to shape the electrodes on the edge of each microchip in such a way that electric fields would connect these microchips, and we could simply transport ions between chips. And now I'm going to show you what followed the idea. We built these microchips, we put them inside a vacuum system, very hard experiment, we didn't know what's going to happen, and now this is the result. So you can see we align these microchips, and now the ions can move across, and now that's the actual experiment. This is microchip 1, 2, we call them Alice and Bob, and you can see the ion moves between these microchips at unbelievable speed. In fact, an alternative technology which was developed at Oxford University and used in America was the state of the art until we did that, and we broke the Oxford record, not by a little bit, but by 7 orders of magnitude. So this technology is extremely powerful in enabling the construction of large-scale machines. You can see that here by adding more and more of these modules together, we can now build large-scale machines with millions of qubits. And now, so these are the numbers here, and this, as I already mentioned, the numbers are pretty impressive. We increased the speed by more than an order of magnitude, but the error rate, and that's really important in quantum computing because errors destroy quantum phenomena. We managed to reduce, as I said, by 7 orders of magnitude. So this is really, really important. And I always felt like maybe things like errors is not really a very intuitive thing. So I was thinking to myself, how I'm going to illustrate this. And we all use elevators, right? Who uses elevators? Perfect. So I'm going to give you the elevator explanation of what we've done here. So the previous technique at Oxford had an error of 6%. So that means if you every day use your elevator, you will get stuck in the elevator once per month. Now, if you use the technology we've invented, and you use an elevator every day, you're going to have to wait for 3,000 years until you get stuck. So I thought that's maybe a good... And so in 2017, we released a blueprint of how we go about building practical large-scale machines that would enable us to really tame millions of qubits in order to solve some of these really interesting problems. And that included creating these electronic quantum computing modules made from silicon microfabrication techniques using standard foundry processes in order to make a quantum computer at that scale. Now you can imagine this is not something you can do in a university. University research grants don't work like that, and you need to get people from Intel, from the major foundries to do so. So we needed to start a company, which we did in 2018. So we founded Universal Quantum, and the company has grown quite a bit. We are now in many countries. The main company is here in Hayward's Heath, but we have subsidiaries in Germany, in the United States, Japan, Denmark. So we're really growing fast. And we got an amazing team. So these are just some of the people here. We managed to get people from Google, from Apple, from Intel, from Mitsubishi, from IBM, from all the major companies, and bring them actually here. And we started this company, investors told us you need to move to the Silicon Valley to do this kind of thing. And we said no, because the UK in 2013 started this National Quantum Technology Program and really did amazing pioneering things here. And so we said, no, we're going to actually do this here in the UK. And this is kind of evidence that this worked, because these people are now coming from the Silicon Valley to us, and we're not going there. And I think that's really nice, and I think that's a really positive thing, especially when you think right now about what some people think is a gloomy time for Britain after Brexit. But here, the UK, Britain is actually generally first and does really amazing things. And I thought that's really great news to know and to hear about. And so the company managed to get a lot of important patents. So we're really doing well in comparison across Europe. And obviously it's not about the number of patents, but the very patents you have. Equally, what we've done in terms of establishing an ecosystem, we partnered up with many companies like Rolls-Royce, Hitachi, lots of really key subsystem manufacturers, Edwards Vacuum here in the region, for example, to create really the possibility to make this not just, because you can imagine as a single company you just can't do this. There's so many challenges you have to master, and so this is really a whole ecosystem approach. We have to work on the programming, the subsystems, all of these things together. And we are merely the system integrator that brings all of these things together. And when you start a company, I mean, I'm sure some of you have done this. It's tremendously scary. I found this immensely scary. I'm a physicist, a professor. That's not what I do usually for a living, to start companies. But we've got amazing help. So the funds, the VC funds that finance us really helped us, and it actually worked pretty well. Now we have more than 100 people in the company. We won the Institute of Physics Startup Award. The next honor I'm not so sure about. We share that with Monzo and OnlyFans, so it's not clear to me about what that means, but we are identified by Bloomberg as one of the top 25 UK startups to watch. But what really made me about a million years the most proudest is that we were placed in the 2024 Sunday Times Best Places to Work list. And that is, for me, wow, that's really made me immensely proud of starting this company, because, thank you. But this is much bigger than just a single company or just a single university. And so what I'm working on right now is to really bring about a whole regional effort together with software developers, with vacuum companies, electronic companies, to make this vision of building utility-scale quantum computers, make this a reality. And so the idea is to really create a whole quantum valley across the M23 corridor, all of East Sussex, West Sussex, all the way to Crawley, brilliant companies like Thales, KG Lesker, Edwards Vacuum, all the Brighton digital scene. There is, actually, you wouldn't know, but here in Greater Brighton is one of the biggest vacuum company clusters in Europe. So this is actually an ideal space, because you can imagine vacuum systems is right at the core of building such technology. And it's also happy to say that government has been immensely supportive, and just last week government announced its industrial strategy and announced 670 million for the development of quantum computing in the UK, again placing it, making it, putting it on track to really be pioneer in this technology. And obviously public investment is only a small component. There's lots of private investment that you leverage. And you're going to ask yourself, why Greater Brighton? Why is this not going to Cambridge or Oxford? This is a good reason, because first of all, the work we do here is really amazing, but it's actually remarkably simple to bring amazing people to Greater Brighton. Much, much simpler to take them somewhere else in the cold north. Brighton, I'm going to have to say, like when I came to Brighton, I had no intent to stay, but I fell in love within a week. Because it's such a wonderful place, and that's actually really important, because you need the best talent from around the world to come. And obviously we are amazingly well connected by Gatwick Airport and by the train line to London and to Cambridge. So this is really amazing. But also in terms of the actual merit of what we do. As a company, we overtook all the other German competitor companies, and we awarded the biggest government tender in Germany to build 2 machines for the German Space Agency. So, and he can tell you, when the Germans do due diligence, they really do due diligence. I had a bit more hair, like when before this started, but it worked out fine, and we now have 5 sites in Hamburg, and we're really scaling up. I should also mention the people who've been supporting us all along. There's amazing venture capital funds. Village Global is backed by Jeff Bezos, Mark Zuckerberg. Hoxton Ventures, you probably kind of use maybe at least once a week, because Hoxton has started Deliveroo, so that's how you might know them. And there's many other ventures. IQT invests in national security, work on behalf of the Five Eyes Alliance of countries. So we managed to get some really good investors helping us to make all of this happen. And I want to really talk about the ecosystem here, which is incredibly important. So all that come from transport, from subsystems development, vacuum, all of that really fits well together. And the regions have understood that. And happy to say that Greater Brighton joint in concert is working now together to make this vision a reality, to really generate what started as academic breakthroughs and really translate that into real economic prosperity. And that means lots of jobs in the area, lots of inventions, and a real high-tech zone, hopefully. And I think that's great. And so I kind of want to end just to say, like, I don't know, who is interested in AI here? So, do you guys know where Geoffrey Hinton did some of his most important work, who won a Nobel Prize for AI at the University of Sussex? And unfortunately, he left. He went to the United States because he didn't feel support here, and now you can see where the benefits went to. Do you guys know where the MRI was invented? So in Nottingham. And unfortunately, I have to tell you, there's not many British MRI companies either. So now is maybe a time to do this differently. And I think here in Greater Brighton, we have a really amazing potential to make this really a reality. So our vision is to create together with all the regions here a whole, and we have to come up with something better, maybe a silicon pier or quantum wheeled or quantum Silicon Valley, something that enables us to really capitalize on this and jointly work together to make this a reality. So and now I don't have that much time left, or probably no time, so I'm going to end here, but I'll leave with you a link to a document where we kind of plot this course of how to make this a reality. Thank you very much.
I told you that was going to be good. Can you imagine if you go to university and this gentleman is your professor? What an inspiring sort of thing to think about every day, going, yeah, okay, I'm going to go and work with that team. So thank you. That's the second time I've heard you talk, and I still don't know how you get an atom in two places. Are there any questions in the audience? There's some questions over here. I'm going to come to you first, there in the front row. Well, it's not the front row, but wherever you are.
I don't know if this question makes sense. I was wondering if it's possible to combine quantum and AI models to have like prediction models that run in parallel. So same way you can have the same atom particle in two places at once, if you could just run predictions in like at the same time, multiple predictions, and just see which one leads to the best outcome, and that way you just find solutions a lot faster.
It's actually it's a very good question, and your feeling is absolutely right. So there is a lot of ideas to think of hybrid systems where you use some quantum computation and in concert. There is actually quantum AI as well. I have to say that's one of the applications that requires the largest numbers of qubits. So that's kind of where we really need big machines. So that's not going to be straight around the corner, but running this in a hybrid way, that's actually something really, really interesting. And so there's definitely a lot of potential. And you can imagine we also use machine learning within quantum computing. So we use classical machine learning to build better quantum computers. And that's something we do in my lab all the time. So AI, machine learning goes really hand in hand together also in terms of the infrastructure. And absolutely, these things will come together and produce in a way much more powerful computational capability where I really capitalize both on the benefits of AI and the ideas of superposition, entanglement that really makes quantum computers so much more powerful.
Question here.
How do you get an atom to be in two places at once?
Yeah.
Everyone take a seat.
So it blows my mind still every day. So, I'm doing this for probably 25 years now. During my PhD, I made an atom move forward and backward simultaneously. That's even stranger, isn't it? So if you hit with your car, both the car in front of you and the car behind you when you park your car. So what we use is actually either lasers, so we put an atom in a vacuum. And that's really important because an atom can't interact with anything else. The reason why we don't see ourselves in two places at the same time, because the air molecules around us, they collapse, we call that collapses into that classical state of me standing here. So the first thing we need to do is we need to isolate the atom, so take all the other air molecules out. And once the ion, so the atom is a charged atom and ion, is completely isolated, then we can use microwaves actually, or lasers. In the past people used lasers, but at Sussex we really invented this whole new technology using microwaves, where now the atom suddenly physically becomes to be in two different places at the same time. And the way we then measure that is essentially we look, for example, where the atom is and what state the atom is, and then we carry out multiple experiments. And as you go through these experiments, eventually you realize the only possible explanation to get to the results you measure, unfortunately, is it was at both places. And I know it still blows me away. So,
go and see it. I don't know how often you open the lab, but honestly, go and see it. You'll still be asking the question. But it's absolutely amazing. Question over here. Here we go.
Thank you. Thank you, firstly, for an amazing presentation. Absolutely inspiring. I met your partner last night, and also love what you're doing in this region. Fantastic. That's way more than just building a company, so that's great. But my question for you is this. Okay, so you're probably the best person to ask this. With your approach, how soon will we get to enough error-corrected qubits, or logical qubits, I don't know what you call them, but to solve some of the world's biggest problems, and then What do you want to see solved first, Borsig?
So in order to solve some of these really hard problems, you need to vastly enhance the number of qubits. What we've done is we've invented this technology that can do exactly that. Now we've got the engineers together to build all of this together, but you can't just do this overnight, because even a standard microchip development cycle is 2 years. So even if you just want to do a custom ASIC, that can just take you half a year or a year, and then you just the ASIC engineer made one little mistake or something, you have to redo that. So don't expect this magic quantum computer to be there next year. We have now the recipe how to do that. Now, the applications really depend. We have a whole application timetable, and if you're interested after, I can tell you a little bit about where these applications sit. Some applications are really hard, need lots of qubits. They might be 7, 8 years away. Some applications may already be 3, 4, 5 years away. Now, I can tell you exactly what I like to do. So I think, fundamentally, if I can have a machine that can help us create better pharmaceuticals much faster and much more reduced cost, I'm going to be very happily lying in my grave and have some little plaque around that man has done that. So that blows my mind completely, because this is something really amazing for humanity. We had an MP actually visiting the company a week ago, and she asked, can quantum computers help homelessness? And I was a bit stunned by that question. Actually, I wasn't even there, but I would have been stunned by that question. But we took this to our algorithm team in the company, and they actually came up with a whole range of things where quantum computers indeed could actually help with that. So things like that really motivate me. Like, I think we need to use quantum computing for the good. You can use quantum computing in all different sectors. Obviously, finance will be an important sector, and there will be lots of investment coming from finance, but obviously that doesn't really blow me away so much. But things like that, like the other thing is, like, imagine you can reduce the energy to make fertilizer. So, I mean, this is like we're all trying to reduce our energy a little bit. Imagine you could do this like in such a profound way. 2% right now of all of the world's energy is for making fertilizer. So things like that, where you have a distinct impact, where you don't just make more money for somebody, but where you can actually really change the world, that would be really cool for me.
One more final question here, I think. Sorry about that. If you can do space-time continuum, then we'll just carry on.
Hi, Winnie. It's Colin.
Hey.
I mean, what you've done is incredible, and you've broken barriers. I mean, I was there with you when you wrote that blueprint, and so your passion's incredible. You built an amazing team, and I wish you every success. I guess I'm kind of interested in, there's obviously lots of challenges. What's the current particular technical challenge that, if you could solve, would move the whole, not just you, but the whole field of quantum computing forward, bring us forward 3 years?
So it's a good question, and there's different hardware approaches to build quantum computers, and each hardware approach will typically have something like a really high-value problem that you need to solve. The good news in trapped ions is there's no hard problem, no physics breakthrough that you really have to make in order to solve a problem. What takes most of our time, and that's actually also really hard, is integrating everything into a single machine. So at Sussex, for example, we have 5 different research quantum computer prototypes, and each prototype essentially is there to develop one particular thing. In one prototype, we make gates a little bit faster. In one prototype, we reduce the power the quantum computer needs, because imagine a small quantum computer, you don't care about power, but if you have a 1,000,000 qubit machine, you really want to make sure you don't dissipate so much power. So integrating all of these challenges into a single device, that's really challenging. And the good news, or the bad news, however you want to call it, this is not just physicists now. This is electronic engineers, that's software engineers, that vacuum engineers, mechanical engineers. So the whole spectrum of people. And this is why the ecosystem is so important. This is not something a university physics professor can solve, but this is really something where we need all hands on deck. So we get some of the best ASIC engineers from around the world, from Intel, from other foundries, to work with us to make these chips, to have little crosstalk essentially between the lines, to have very low noise, digital to analog converters. None of these things we need to push the specification beyond what has already been achieved, but we need to all integrate them into these electronic quantum computing modules that you have seen and really build a product, not a university experiment. And so this is kind of, for me, is also super exciting, because I'm now half-half. I'm 50% company, half university. And the university, I can do mad things and press buttons and make things explode. And however, in a company, the engineers tell me exactly what I need to do and what I'm not allowed to do. And so bringing all these two worlds together for me is absolutely wonderful. And so I'm learning so much from the engineers that work with us, the software engineers, all the great teams, and also from our partners, from people like Rolls-Royce or Edwards Vacuum and KT Leske, and all these companies that really help us to make this vision a reality. And only together that can be done. And so that's why I'm so interested in making this a regional thing. Also the software, the training, all of that needs to come join together in order to make that vision a reality.